So we were discussing entropy. Entropy means disorderness of any system. So we were discussing this, right? So, and why do we discuss entropy? I told you that basically the purpose of discussing entropy is to tell the spontaneity of reaction, whether the reaction is spontaneous or whether the reaction is spontaneous or non-spontaneous. So we have to discuss this, okay? So let's suppose, let's suppose, um, spontaneous, generally we say that exothermic reactions in which the products has a lower energy, because in an exothermic system, the energy is being released from system to surrounding. It means that the energy of the product is lower. So means that this is going to be more stable reaction. So this is observed that these reaction occurs on its own. Yeah, like nothing, no energy should be provided. Let's suppose, let's suppose if you have sodium, piece of sodium metal, and just you take sodium metal into an open atmosphere and just you are going to wait for 1 to 2 minutes. Since sodium is very reactive, so automatically it would be reacting with oxygen and it would be forming sodium oxide. So means that this is spontaneous reaction. So I'm telling you that it's a general observation that exothermic reactions are spontaneous reactions. They don't require energy for startup. I can say activation energy is not necessary for these reactions. Okay, so that's why I'm saying that these reactions are spontaneous reactions. And generally, for those reactions which are endothermic reactions, right? So for an endothermic reaction, I can say that they are non-spontaneous. You know, for an endothermic reaction, I can say they are non-spontaneous. But But this is not a criteria to decide whether the reaction is spontaneous or non-spontaneous. You know why? Because we have some examples that despite they are endothermic, but they are spontaneous. We have some examples, like let's say if you are going to dissolve sodium chloride in water, if you are going to dissolve sodium chloride in water, it will dissolve. It will dissolve automatically. You are not supposed to stir. You are not supposed to provide any sort of temperature. It will dissolve automatically. But yes, it will take time. It will take time. Let's say if you are going to dissolve lump of lump of sodium chloride. Let's suppose if you have a large piece of sodium chloride and you are going to dip this sodium chloride into the water and just you are waiting for 5 to 10 minutes or for 15 to 20 minutes, it will dissolve automatically, but it will take time. So I can say that this reaction is spontaneous, isn't it? This reaction is spontaneous, but the thing is, this is endothermic. So I was telling you that endothermic reactions are non-spontaneous and exothermic reactions are spontaneous. So this is not the criteria always that, like, we cannot fix it that all the time exothermic reactions are spontaneous and endothermic reactions are non-spontaneous. No, that I told you this is an example of endothermic, but this is going to be spontaneous. So we need to have some other thing. We need to have some other factors. On the basis of that factor, we can decide whether the reaction is spontaneous or non-spontaneous. That's why we discuss entropy change. Remember, this is the this is the theory that why do we discuss entropy. So entropy is a better tool to discuss the spontaneity of any reaction. Remember, okay. So let me tell you this one that um, generally, generally, exothermic reactions generally exothermic reactions are spontaneous and endothermic reactions are non-spontaneous, right? And endothermic reactions are non-spontaneous. And by the way, spontaneous is the term which means that, let's say, if I'm going to describe the term, spontaneous means what? When the reaction happens on its own, like no external energy is needed, no external energy is required for these reactions. So I can say that the reaction, the reaction which occurs on its own, on its own, no external energy is needed. No external energy is needed. So if this is so means that the reaction is spontaneous. Okay. Um, and then, um, as I told you that we need to discuss the entropy change to describe the spontaneity of any reaction, right? So let's say if we are going to dissolve sodium chloride in water, see this one. Let's say if I have a water molecule in which I am going to dissolve sodium chloride, in which I am going to dissolve sodium chloride, and it's going to be solid. And in this beaker, I have water molecule. And in this beaker, I have what? I have water. So when sodium chloride will be dissolving in water, you will see that in this beaker there would be a lot of cations and a lot of anions would be there, isn't it? Because sodium chloride has been dissolved. It's an ionic compound. Ionic compounds have a good solubility in water. Okay. So I can say in other words, I can say in other words that ions are disordered. Ions are disordered, or I can say dispersed. Because when sodium chloride was in the solid state, like they were not random, they were fixed at a fixed position. Because we have learned in chemical bonding that ionic compounds have a giant ionic lattice structure in which we have a lot of cations and anions that are held together with a very strong electrostatic force of attraction. Even they cannot move. Even they cannot move. So means that they are not random. Entropy is lower because entropy means when something is in disordered, like when something is disordered. It's a study of disorderness of any system, randomness of any system, I can say, right? So entropy is nothing but its disorderness. It's what? Disorderness of any system, or I can say randomness of any system. Okay. So when I'm saying that the ions are dispersed, the ions are disordered, so I can say the entropy would be higher. The entropy would be what? Higher. So this property is known as, so this property is known as entropy. So this property is known as entropy. So entropy is nothing but it's the disorderness of any system. Okay. Um, so when the entropy will be increasing, remember, when the entropy increases, like you can see this one, Entropy is going to increase in this system. You know why? Because the ions are going to be more random. And by the way, entropy is represented by capital S, right? Entropy is represented by capital S, and the unit for the entropy would be, joules per mole per Kelvin. This is the unit for the entropy. Okay. So in this case, I can say entropy increases. Entropy increases. Okay. So the energy is distributed into these ions. When the energy is distributed, so means something is going to be more stable. So that's why the reaction is spontaneous. So it's better to discuss the spontaneity of reaction in terms of entropy change. It's not about it should be exothermic or it should be endothermic. No, because we have a lot of exceptional cases. As I told you, one example in which sodium chloride was dissolving spontaneously and it was endothermic. So this is how we have introduced entropy term. So on the basis of entropy, from now onwards, we would be deciding the spontaneity of any like reaction. Okay. So, and remember, examiner will be asking to find out the entropy change, to find out the entropy change. So let's say initially I have entropy of sodium chloride that was very low. I can nominate it. Let's say I'm saying entropy is lower for solid sodium chloride. Entropy is lower. And in this one, entropy is higher. So we have to discuss the entropy change. We have to discuss the entropy change. Remember, an entropy change is represented by delta S. An entropy change is represented by delta S. Remember. So that's going to be what? Entropy, entropy change. And entropy change is nothing but it's the delta S. And you know this symbol, you know what does it mean? It means that at a standard condition, at a standard condition, simple. So I can say it would be a standard entropy change. It would be what? Standard entropy change. If you remember, we used to discuss standard enthalpy change of formation. What was that? When 1 mole of a compound is formed from its elements in their standard states under standard condition. Under standard condition. So that was what? Standard enthalpy change of formation. So this is going to be the same. This is called standard entropy change. So examiner would be giving you different reactions and he would be asking whether the entropy is increasing and whether the entropy is decreasing. So then we have to see in that reactions. Let's say I'm giving you this reaction in which water liquid is turning into water vapor, H2O gas. So, you can see in liquids, the particles are come closer to, like the particles are just close to each other as compared to the gas, because in the gas, the particles are far away from each other. So I can say they are more random, isn't it? They are more random and they are less random and they are less random. So yes, entropy change is positive. Entropy change is positive. Remember, entropy change is positive. And whenever the entropy change is positive, so the reaction is spontaneous because disorderness is going to be increased. Okay. And let's say if I have a water molecule at room temperature, evaporation will start. Evaporation doesn't require any specific temperature. Evaporation occurs at any temperature. So what do you mean by this? Because we are not going to do anything else. We are not providing temperature. We are not providing a catalyst. We are not providing a pressure. We are not going to give any sort of condition. This is going to, like, this is happening on its own. No external force is needed. So yes, this is purely, we can say, a spontaneous reaction. You know why? Because entropy change is positive. And can you expect that the gas is going to be converting into liquid spontaneously? No, no, you have to decrease the temperature. Have you ever listened that the gas is converting into the liquid at room temperature? It's not possible. It's not possible. It's non-spontaneous reaction. And for a non-spontaneous reaction, what would be going on? Let's say if I'm asking the something is converting from gas to liquid, means that the particles are coming close to each other, more disordered to less disordered. So what does it mean? Entropy is decreasing. Entropy is negative. So yes, I can relate the entropy with the spontaneity of a reaction. If the entropy change is negative, so the reaction would be non-spontaneous. And if the entropy change is positive, so the reaction would be spontaneous. Remember. Okay. So uh, relation between entropy and the spontaneity of reaction. What is that? So if the entropy is positive, if the entropy is positive, I would say that the reaction would be spontaneous. The reaction would be spontaneous. And if the entropy change is negative, so I would say that the reaction is non-spontaneous. A lot of questions you would see related to spontaneity, spontaneous, non-spontaneous, spontaneous, non-spontaneous. So what we have to do, we will be determining the entropy change. Sometime we can look at the reaction and we can determine the entropy, whether the entropy is positive or negative, and sometime he would be giving you the value and we can calculate the value. It's just like we did the enthalpy change. It's the same, 100% same. If you remember, uh, we have calculated the delta H. The formula was product minus reactant, and the same goes for the bond energy. So we did the bond energy. The formula was reactant minus product. In the same way, we will be applying the formula for the entropy change. So the formula would be product minus reactant. I will be telling you later on. So, so right now, let's say I'm giving you the reaction in which magnesium would be reacting with HCl, and it would be giving you magnesium chloride and hydrogen gas. State symbols are important. It's going to be solid. This is aqueous. This is aqueous. This is gas. This is gas. Remember. Okay. So if this is gas, so I can say that overall entropy is increasing, isn't it? Overall entropy is increasing. If overall entropy is increasing, so I can say the reaction is spontaneous, isn't it? Overall entropy is increasing. It's changing from solid to gas. It's changing from aqueous to gas. So yes, I can say that entropy is increasing. I can say entropy is increasing. And if the entropy is increasing, so means that delta S is positive. And when the delta S is positive, so yes, on the basis of delta S, like of course, when the delta S is positive, so the reaction is spontaneous. If the delta S is positive, so I can say that the reaction is spontaneous, right? Let's say if I'm asking N2 plus 3H2, it's going to give you 2NH3. It's a very famous reaction, Haber process. What do you think about this reaction, whether the reaction is spontaneous or non-spontaneous, and whether the entropy is positive or negative? Okay, so I have, this is the gas, this is the gas, this is the gas. So total number of moles are 4, and this is the total number of moles, that is going to be 2 moles and 4 moles. So total number of moles of gases are decreasing. When the total number of moles of gases are decreasing, so randomness is going to decrease. When the number of moles of gases, when the number of molecules of gases are higher, so the randomness would be higher. And when the number of moles of gases are lower, so the randomness would be lower, isn't it? So yes, delta S would be negative for this reaction. You know why? I would say that number of moles of gases are decreasing. Number of moles of gases are what? Are what? Decreasing. Remember. So yes, I can say the entropy is going to be negative. Okay. And what if I tell you, let's say this is the first example, and then we have another example, then we have another example. Let's say I am saying copper sulfate dot 5H2O. This is hydrated copper sulfate. I'm going to heat it. I'm going to heat it. It's going to be copper sulfate plus 5H2O. Okay. This is going to be gas, and this is going to be solid. This is going to be hydrated copper sulfate. It's also solid at room temperature, by the way. Okay. Now I'm asking, what do you think about this reaction? Whether the reaction is having entropy positive or negative. Okay. So the overall entropy is going to increase. You know why? You know why? Gas is introduced. Randomness is going to increase. Randomness is going to increase. Okay. So, so you have to see the particular reaction what the examiner is asking. So he will be giving you different criteria. Sometime let's say in a question, sometime he asked, what would be the sign of entropy change when acid reacts with base? Listen carefully what he is asking. When acid reacts with base, like I'm talking about the neutralization reaction. In a neutralization reaction, what's going on? If you will be writing down an ionic equation, so this is going to be ionic equation for a neutralization reaction. You have discussed this in IGCSE. It's a basic equation. Ions are reacting with each other. H positive is going to represent acid, and OH negative ion is going to represent alkali. That is going to be base, isn't it? And as a result, I can have water molecule. So from, H positive, what's the state symbol? Aqueous. OH negative, what's the state symbol? Aqueous. H2O, what's the state symbol? Liquid. Aqueous to liquid. Entropy is decreasing. Delta S is negative. Remember, delta S is what? Delta S is negative. So we have to see these all conditions. Remember, we have to consider all of the conditions. So from now onwards, you must know how can we determine the sign of the entropy change, whether the entropy change is positive and whether the entropy change is negative by looking at the reaction. Let's say ice melts. Let's say ice melts. So ice was solid. When it would be melting, after melting, it would be converting into liquid. So overall, what's the what's the change? Of course, solid to liquid. So means that the randomness increases. So the entropy would be positive. Okay. Water boils, water evaporates, water evaporates. So when water evaporates, what's the overall change? Evaporates means that it changes from liquid to gas. It changes from liquid to gas. Remember, okay? So entropy change is positive. Entropy change is positive. Remember. So the thing is that we have to discuss the spontaneity of reaction. We have to see the second law of thermodynamics. What the second law of thermodynamics means that reaction can be spontaneous. Reaction can be spontaneous if the total entropy change is positive. Remember, what the second law of thermodynamics says, the reaction can be spontaneous if the total entropy change is positive. You know what he is talking about, like the total? Total means that entropy of the system and entropy of the surrounding. So remember, um, from second law of thermodynamics, from second law of thermodynamics, he says that reaction can be spontaneous. Reaction, reaction can be spontaneous if the total entropy change is positive. Okay. If the total entropy change is positive. And what's the total entropy change? And what's the total entropy change? So the total entropy change is delta S of system plus delta S of surrounding. Delta S of system and delta S of surrounding. Okay. So we have to consider these two entropies and we can calculate these entropies very easily. So if we want to calculate the entropy of the system, so this is the formula. Sum of all the entropies, sum of all the entropies of the product minus sum of all the entropies of reactants. In other words, I can say product minus reactant. Same as delta H. Same as, if you remember, same as delta H is equal to product minus reactant. Okay, nothing is new. Nothing is new. The formula is same, but the name is changed. We used to say that this was delta H, and today we are saying this is entropy change. Formula is same, product minus reactant. Okay. So how can we calculate the entropy like change? So let's say I'm giving you the reaction, that is calcium carbonate. When it decomposes, it's gonna give us calcium oxide plus carbon dioxide. This is solid, this is solid, this is gas, isn't it? This is gas. So can you identify Can you predict the sign of entropy change without the calculation? Yes, I can predict the sign of entropy change without calculation because overall, what's the change? It's from solid to gas. It's from solid to gas. So the entropy change would be positive. So the entropy change would be positive. So we can predict the sign of entropy change without calculation. Okay. So I was saying that the values would be provided just as in this reaction. I have given you the entropy value for the calcium oxide, that is this one. For the carbon dioxide, this one. And for calcium carbonate would be 92.9 joules per mole per Kelvin. After having the values, I can apply the formula, that is product minus reactant. Delta S is equal to product is 39.7 plus 213.6. This is product minus reactant side is 92.9. If you will be calculating this one, so you will be getting the answer plus 160.4 joules per mole per Kelvin. This is the answer for the entropy change. And this is positive. As I told you that, without calculation, we can predict the sign of entropy change. That is going to be positive. You know why? Because overall it's changing from solid to gas. We can predict it, but of course you will be having the marks for the calculation. So you must know how to calculate the entropy change. Let's say I have another one that is Haber process. In which N2 plus 3H2 and then 2 ammonia molecule. Gas, gas, and gas. Can you predict whether the entropy change would be positive or negative? Yes, I can predict because the overall number of moles of gases are decreasing. Means the randomness is decreasing. When the randomness decreases, so the entropy change would be negative. We can further confirm it by calculating the entropy values. So I am giving you the values for the nitrogen, hydrogen, and ammonia. The entropy change for the nitrogen is going to be uh, 191.6, 191.6. All are in joules per mole per Kelvin. And entropy change for hydrogen would be 130.5, again with the same unit, joules per mole per Kelvin. And the entropy change for the ammonia would be 190 2.3 joules per mole per Kelvin. Okay. So now I'm going to calculate it. Since we know the formula, that is product minus reactant. Product is ammonia. So the value for the entropy of ammonia is 192.3. Since the coefficient is 2, I'm going to multiply this by 2. I'm going to multiply this by 2. Okay, this is my product minus reactant. Reactant is N2. N2 is 191.6 plus. Then we have hydrogen. The coefficient for hydrogen is 3. I'm going to multiply hydrogen by 3. It's going to be 130.5. After calculation, after calculation, I got the number that is 198 negative joules per mole per Kelvin. So yes, uh, entropy change is negative. So this is the way that you can calculate the entropy change for the system. Remember, for the system. And what about the entropy of the surrounding? What about the entropy of the surrounding? So yes, we can also calculate entropy of surrounding is equal to entropy of surrounding is equal to negative delta H over T. T for temperature in Kelvin. Temperature in Kelvin. And delta H is what? It's an enthalpy change. Delta H is what? It's enthalpy change. And T means it's the temperature. It's not time. It's temperature. In what? In Kelvin. Okay. So, um, let's say, let's say if a reaction is exothermic, listen carefully. If the reaction is exothermic, okay, of course, the reaction is releasing energy. The reaction is releasing energy. Okay. And the energy is going to the surrounding. Got it? Energy is going to the surrounding. So I can say the temperature of the surrounding increases. Okay. The temperature of the surrounding increases. When the temperature of the surrounding increases, that's why, if you remember, in a previous basic classes, we used to say, when we were discussing exothermic and endothermic reactions, we used to say container becomes hot in an exothermic reaction and container becomes cold in an endothermic reaction. Why? Because in an exothermic system the energy is released and the surrounding is what? Is the wall of the cup in which you are going to do a reaction. Let's suppose I am having a cup of hot tea. So can you touch that cup? It would be hotter. You know why? Because the wall of the cup is your surrounding and the T is your system. The system is releasing energy. Surrounding is absorbing energy. So the temperature of the surrounding increases. When the temperature of the surrounding increases, so entropy of the surrounding increases. I'm talking about exothermic reaction. And what about for endothermic reaction? In which energy is absorbed. So what do you mean by this energy is absorbed? So I can say entropy, I can say the temperature of the surrounding decreases. You know, if you remember, for an endothermic reaction, the container becomes cold. The container becomes cold. Okay. So when the container becomes cold, so the temperature of the surrounding decreases. When the temperature of the surrounding decreases, so the entropy of the surrounding will decrease. So it's the relationship between the entropy and the temperature change. Okay. Uh, and how can we calculate the entropy of the surrounding? Let me tell you a question. So let's say find uh, let's say find delta S of surrounding. Okay. Find delta S of surrounding when 1 mole of hydrogen gas is burned. When 1 mole of hydrogen gas is burned. So at 298 Kelvin, this is the reaction. Hydrogen plus oxygen burning means combustion. Combustion means oxygen is mandatory. Hydrogen is reacting with oxygen. It's going to form water. This is liquid. This is gas. This is gas. Can you predict the sign of the entropy change without changing the, without calculating the entropy? Yes, I can predict the sign of this entropy change because gas is converting into liquid. Like the randomness is decreasing. When the randomness decreases, so the entropy decreases. So the entropy change would be negative. So the entropy change would be negative. So, the delta H is given for this reaction, that is negative 286 kilojoules per mole. We know the formula, that is delta S of surrounding is equal to minus delta H over T. Negative, and the sign for delta H is also negative, that is going to be 286 divided by the temperature, that is 298 Kelvin. So the answer would be positive 0.960 kilojoules per mole. Joules per Kelvin per mole, basically. So since the value was in kilojoules, so it's gonna be kilojoules per Kelvin and per mole. Kilojoules per. Now you're thinking, sir, you were saying that the entropy would be negative, but it's positive. So, the thing is that we have to see the overall answer. Like I'm talking about the delta S total. Delta S total means, you know what? It's the sum of system and the surrounding. If the sum of system and surrounding would be positive, then I can say, like, I can predict the sign of the entropy change. I can't like select any one of them. I have to see the overall change. Remember, I have to see this because when the examiner would be asking these things, so it means that you have to know the overall entropy, means total system plus surrounding. So we have different methods to calculate the entropy of system and the entropy of the surrounding. We can calculate entropy of system by applying the formula, that is product minus reactant, and we can calculate the entropy of surrounding by applying the formula delta H upon T. Okay, so we have different formulae. We are getting the different answers, and in like after calculating system and surrounding, we can add these two entropies to get the total entropy. Okay, because total entropy is system then plus surrounding. Okay, got it. So let me tell you in which the examiner is asking. It's an old paper. It's an old paper, but we can see some questions related to related to entropy. Yeah, you can see this paper. You can see this paper. Okay, 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 okay. Hmm. Yes, question number three. Question number three. Yes. What do you think about this reaction? Which reaction has the most positive entropy change for the system? Most positive change for the entropy of the system. Yes, what do you think? Which option should be correct? Yes. Mm-hmm. Mm-hmm. Iman Manal. Yes. Mm-hmm. What's the answer?
Is it C?
C means 2 moles of gases. See? It's negative. Gas to liquid. They are asking positive. Mhm, mhm.
Is it D?
D for doctor. Okay. D, 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 D. Yes, good. D is correct because 1 mole to the 2 moles when the number of moles of gas increases. So the randomness increases. So entropy would be positive. Good, 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 good. Okay. And what about this reaction? Yes. Barium carbonate decomposes in an endothermic reaction when heated to 1500 Kelvin. So this is the reaction. What are the signs of the entropy changes at 1500 Kelvin? They are talking about delta S of system and also the delta S of surrounding. By the way, this is an endothermic reaction. Energy is absorbed. So I told you in an endothermic reaction, the temperature of the surrounding decreases when the temperature of the surrounding decreases. So the entropy of the surrounding decreases. Remember, so the entropy of the surrounding decreases. So after thinking about that, what do you think? What should be the correct answer for this reaction? Yeah, this is understood that the entropy of the surrounding decreases. So it should be B, it should be D, B for ball, D for doctor. It shouldn't be A and C because in A and C, entropy of the surrounding is positive. How is that possible? Entropy of the surrounding is only positive when the reaction is exothermic. So we have to see B and D. What do you think? It should be B or D?
D.
It should be B for ball, not D for doctor. You know why? Because for an endothermic, energy is absorbing, energy is being absorbed. When something is absorbing energy, it means that the temperature of that substance increases. When the temperature of that substance increases, so means that the entropy would be increasing. So for the system, entropy would be positive, endothermic, for endothermic, and for the surrounding, the entropy would be negative. You are supposed to note these points. It would be very helpful for you. You are supposed to write down the both, like for endothermic and also for the exothermic. We have a lot of questions related to this, for exothermic, for endothermic, for exothermic, for endothermic. So you must know both of these. You can write it down like for endothermic, entropy of the system is positive, entropy of the surrounding is negative, and for exothermic, entropy like vice versa. Simple. This is also easy question. This is also easy question. They are asking the entropy change of the system. Yes, we know the formula. We know the formula. Product minus reactant. Product minus reactant. Okay. You can also solve this one. Then he is asking to calculate the entropy of the surrounding. And then see this. Total entropy. 2, then 2, then 2. 6 marks and it's nothing. Literally, it's nothing. Honestly, it's nothing. It's very easy question. Just you have to see the values, what they have provided to you, and just you can calculate it. And then whether if he would be asking about the like entropy change or is positive or negative, so you can discuss it. Okay. If this is going to be positive, so reaction is spontaneous. And if this is going to be negative, so reaction should be non-spontaneous. Okay. But interestingly, you know, I have started this chapter from the enthalpy change. You know what I was saying? Enthalpy change means when there is an exothermic reaction, so the reaction should be spontaneous. And when this is an endothermic reaction, it should be non-spontaneous. But it's not true. They are not going to give you 100% true result all the time. I gave you an example of sodium chloride. so so that's why it's not a good tool to identify the spontaneity of reaction. We have introduced the term entropy, and afterwards I would be saying to you entropy is also not a good uh, tool to identify the spontaneity of reaction. We have the third term that is called Gibbs free energy. This is the full and final decision. After looking at the Gibbs free energy, we would be uh, what can I say? We would be identifying the spontaneity of reaction. So entropy is not reliable. Delta H is not reliable. So that's why in the last, we will have to discuss the Gibbs free energy that is going to give you the reliable source to predict the spontaneity of reaction finally, whether the reaction is spontaneous and whether the reaction is non-spontaneous. So we need one more class for this one, like I'm talking about the spontaneity, like Gibbs free energy, and then that would be enough for this entropy change. Then we can start the next chapter. Okay.